think for the recording it's really bad. There will be no sound at the moment, but I think everybody's catching me. So, okay. We talked about transport the last time, and we realized that transport can be of many different ways. We can think about transport as equilibrating the intensive property associated with the number of particles, meaning concentration. Really, what we're equilibrating is chemical potential, but chemical potential of the species is equilibrated by equilibrating concentration. Or we can think about as transport equilibrating pressure, the intensive property associated with volume. No matter which of the two is the case, we find we have the same diffusion constant in a way, which governs the sum of that. And if you're looking at the transport of particles and the movement of particles, we also again have a diffusion constant. So this diffusion constant over here is very, very important. It relates to how far do particles travel by themselves. It relates to how concentrations equilibrate if we have the barrier removed. You can find diffusion constants for anything and everything. And no matter in which field you are going in chemistry, they are relevant for you. I'm more on the physical chemistry side, so my interest is more in physical applications for that. So let's say if I were to make a semiconductor of a particular property, I might want to have a p-doped or an n-doped semiconductor. If you leave back in the handouts and figure out what they were. The way they are made, at least the way they used to be made, is that you put the dopants on top of the semiconductor and then you heat up the semiconductor, letting them diffuse internally. So the diffusion of those atoms inside the solid to equilibrate the concentration between dopants, high on the surface and low, at least initially in the material, it's just a diffusion problem. And Fick's first law is used to model. People figured out how deep can the dopants diffuse into the material by looking at Einstein-Swarovski's equation in order to figure out how deep will they get. And then they looked at the diffusion constants of atoms of species in solids. And they are, of course, much, much smaller unless you heat the solid very high up, and then they can approach the other condensed phase, that one, the liquid phase. So that is one application of diffusion. Another application of diffusion is, of course, in the biological field. As you go smaller and smaller in objects, diffusion becomes comparatively faster and faster because of this root kind of dependence. And so the smaller the organism you're looking at, or the smaller the cell you're looking at, the more you'll find that diffusion plays a crucial role in equilibrating concentrations and in transporting material from A to B. Only if we are large, we need to have something which then isn't governed anymore by Fick's first law, but rather is governed by Poiseuille's law in order to transport volumes of an object from A to B. That is only required, that is only something really relevant if we are at a larger length scale. If you're at the smaller length scale, diffusion is a rapid process and we don't need to worry about having things transported by diffusion. But as we get to the scale of the Earth, we have winds on that. That is viscous flow, that is now difference in pressure at different locations, which makes the whole volume flow rather than only individual atoms moving. Or put in a different way, if I were to average the velocity of all the particles in a certain volume, if that average becomes 0, then I have diffusion. Then I have the same number of particles going left and right. Might be different kind of particles if I have a concentration gradient, but it's still the same number of particles, or approximately the same number going there. But if that average becomes a non-zero number vector, then I'll have viscous flow. Then on average the volume travels with a certain velocity. And then I'll talk about flow, or wind, or whatever the context is. And you talked about fluid transport the last time. It is a diffusion equation. It's the same kind of equation which we had for Fick's first law. It is the first derivative by time of an extensive property of a system equals the first derivative of an intensive property, the pressure, by the position, the location where we are. And then you put in factors in front of the minus sign because you always go in the opposite to the gradient. And then something which corresponds to the size of the cross-section to which the flow occurs. And that goes squared. Square the cross-section with force, power, and R over here, because on the one hand side, there's a linear relationship with cross-section. If the tube is twice as big, then twice as much flow can happen to that. But then there's also this behavior that the particles which are at the edge of the tube, they constantly bounce against the static walls over here and get slowed down. Whereas the particles more towards the center of the tube, they bounce only against the neighboring particles in the movement, and they are already moving, and so they're not so much slowed down. And so I'll have this quadratic kind of flow profile inside the tube. And so I will have a quadratic order in the radius for this, and quadratic in order to get the cross-section or to get the force power. Now, the constant which is governs this here is the viscosity atom. This is Greek letter atom over here. You work from over with that. There are values, and the values for viscosity are for no particular reason given in centipoise. It's just the poise, P-O-I-S-E, that is the big P over here, and the centi, like a centimeter, hundreds of that. And the real reason why that is that it's close to 1 for water, if you find it. And the centipoise is not too far away from its I units. It's a millinewton a second per meter squared. So the centipoise over here is the millinewton into the minus 3 newton seconds per meter squared. So viscosity is the friction of a liquid or a gas when it flows. So it's very related to this kind of friction when I'm dragging something across the surface. It's just there's no surface and a rigid object which you drag, rather than it's the liquid which you drag through the tube. Okay, that gives us then Husserl's law. In Husserl's law, if you increase the pressure by 2, the pressure difference, if you had twice as much pressure difference, not 25 psi but 50 psi in your homework problem, you would have twice as much flow everywhere. So it's a linear relationship with the pressure. But if you were to change the radius of any of those parts, then it's a force power of that. So it goes up with the force power. So if you put the two in one graph, you can see that doubling of the radius will 16-fold increase your flow rate, whereas doubling of the pressure will just 2-fold increase your flow rate. So there's a limit of what you can achieve in changing the flow rate by the pressure. But if you change the radius of your tube, then you have a very, very sensitive dependence of the flow rate on that radius. There's one caveat to this, and that is gas transport. So far, we looked at the transport of a liquid. Husserl's law really only works well for the transport of a liquid. If I have a gas, then things become a little bit more complicated. The reason why things become more complicated is that if I have the gas and I'm trying to transfer that from an area with high pressure to an area with low pressure, then the gas needs to flow through this cross-sectional area over here just as the liquid happens. But the amount of gas which flows through this cross-sectional area, or to that cross-sectional area, or to that cross-sectional area over here is different. Because as the pressure is getting lower, the gas will expand. And so here there's very little gas which needs to be transported. And then if the pressure is a variation of 2, maybe this is twice the pressure here than it is over there, then we need to have twice as much flow of the gas over there. It's twice the volume, because the volume of gas is proportional to the pressure. So it gets really complicated with that, because the volume of the gas keeps increasing as the pressure is getting lower, and as a consequence you need to transport more on this side than you need to transport on that side. But if you have a straight tube, how do you do the math? You don't do it. So there's something called the Navier-Stokes equation, which would then allow you to calculate those things, but that is only a fairly complex three-dimensional differential equation, which we are not going to cover. If you were a chemical engineer, then you would have to learn a lot on how to deal with that. That is what chemical engineers do. They try to set up reactors and flow them and mixing them. So there are lots of chemical engineering classes which will teach you a lot about that, but not this. So you might approximate it this way or that way it's not a very good approximation. So the real takeaway message is if you have significant pressure changes between the starting place and the end place, calculating how much flow you have in a tube is a really complex problem. There's one more, viscosity. Viscosity we talked about is the friction, the resistance. And just like the diffusion constant, if I have small spherical particles, they can squeeze by each other very easily. If I have large odd-shaped particles, like the dodecane molecule, they will kind of entangle each other here and have a hard time moving. And as a consequence, here you have a high viscosity, there you have a low viscosity. If you have more interaction between the particles, it's harder for them to slip on each other. Then you have a high viscosity. If you have little interaction between the particles, you have a low viscosity, and so on and so forth. Many different variations. I think you did an experiment already in some lab about viscosity, where you dropped spheres down and measured how fast is the terminal speed. And the terminal speed is of course determined by the drag or the flow resistance that this sphere of known mass experiences while it is moving. So it is measuring a property of the liquid over here, how much the liquid needs, how much friction there is in the liquid to part away to let that ball fall through it. And so just studying how the sphere falls down, you can get a fairly good idea about the viscosity of the material. It's not a perfectly good idea, but it's a fairly good idea. Better results you get with Oswald, as I'm showing it here, viscosity, where you measure how long it takes for a certain amount of liquid to pass through a thin tube. Then there are also torsion-based viscosimeters, where you have a spring which you keep rotating, and the spring tries to spin inside the liquid, and that was then measuring how much resistance there is to the spring. It also gives you an idea of viscosity. So there are many different ways about measuring viscosity. Viscosity might sound arcane to you, and why would you care about viscosity? But then, from a technical point of view, there are lots and lots of places where viscosity is super important, and where chemists are involved. Think about motor oil. Clearly, the viscosity there is super important, because that is really what the oil is supposed to do. provide lubrication and not be in the way of the moving parts. So it needs to have a low viscosity. But also think about all the food items we buy after they have been processed in some way. So if it were even tomato sauce somewhere in any of pre-prepared food that needed to be somehow placed on that pre-prepared food, and so it needed to have a certain viscosity so that the machine can dispense it in the right way. So viscosity measurements are anywhere and everywhere. They're super, super important, even though if we don't think too much about it, it doesn't appear to us as a very abundant problem. The next thing I have to talk in this context is laminar and turbulent flow. Everything we did so far was for laminar flow only. Laminar flow in this Bunsen burner flame you can see in the bottom over here. But all volume elements just move in the same direction in parallel over here. So they just move all kind of parallel to each other down. The opposite of laminar flow is turbulent flow. And turbulent flow you'll find up here. Why do you have a transition from laminar to turbulent flow here? There are two reasons for that, at least. One reason is down here the gas is still cold. The combustion hasn't happened yet. If the gas goes up over here, the combustion takes place, meaning the gas is now being heated. PV equals NRT means the volume of the gas expands because the pressure is all the ambient pressure over here. So down here, it's fairly little gas which needs to be transported in this flame. Up here, it's a much larger amount of gas which needs to be transported because now the heating of the gas as a consequence of the combustion increased the volume. It might also be that out of few volumes of reactants, you create more volumes of product in that, and that way you even need to transport more gas. If you had a butane flame, then for one butane molecule you might make like 10 product molecules. So you have much larger amounts of gas which needs to be transported up there. And lastly, the behavior of the gas particles up here is also a little bit different because they are now at higher temperature. They go with a higher speed in every which direction in addition to their laminar flow. And so they might cause more turbulences as well. So the laminar flow, all volume elements move next to each other. In a turbulent flow, they don't. In a laminar flow, we can calculate the amount of material which we transport by Bousseur's law, and in a turbulent flow, we can't because there are not any more movement so much. We don't have a clear flow profile. We have a transition from laminar to turbulent flow as we exceed a certain threshold amount of flow. If we have small amounts of flow, the flow will be laminar. If we increase the flow will transition to turbulent. Again, something super important. Just imagine if you have these kind of eddies and turbulences in your water pipe or in your gas pipe going to your house, it would bang and so on. It would not be good. So different burners, you can always see very nicely laminar flow, turbulent flow transitions. But you don't need to look at the Bunsen burner in order to do that. You can just look at the freeway. On a freeway, people must behave like gas molecules. And if you have few enough people on the freeway, you have everybody going in the lane straight up. But at some point, you try to transport too many gas particles, people on the freeway, and you have to transition to turbulent, where people don't go all straight anymore, but change lanes, and you get effectively a smaller transport, more resistance to transport. And you can study that the behavior of the particles, being in people in car or being in gas molecules, essentially follow the same laws. Now, another reason why we need to consider transport of hot gases is steam. Now you might think steam engines was an old technology, and that was many, many years ago, and why it's relevant for me, except for looking at carry hotter centers. The reason for why we need to consider steam is that steam is still the important part in transporting heat inside any chemical, any factory, any refinery, everywhere in chemistry, in bulk chemical. So if I have one reactor in a refinery or somewhere in a chemical plant, and I'm creating heat over there, I don't want to waste that heat because some other reactions will need extra heat in order to move forward. So what I really want to do is I want to transport the heat from one reactor to another reactor. And the way of doing that is by means of steam. You don't use just hot water because many of those reactions work at 200, 300, 400 degrees centigrade. And then so water is only one phase, one state of liquid water is only one phase, one state of that. So often you have then a transition that water becomes steam and you transport the steam. So if you think about bulk chemistry, even commodity chemistry stuff, it's all about transporting steam in order to create efficient processes. And so we need to be able to understand how we transport the steam from one place to another. And again, we'll come back to Poisson's law. The real challenges then is that there is this phase transition between vapor and liquid, between steam and liquid water. And many odd things can happen if you have flow. If the flow becomes turbulent, in the turbulent flow you have these kind of eddies over here, and if those eddies are associated with a larger and smaller pressure, then you can have phase transitions of the steam or whatever you're transporting from the liquid to the gas phase and vice versa. And that is like an oscillator. It can oscillate more and more and more and more, and it can come to things like this. This is a picture from New York City, which is, if you wish, Manhattan is like a chemical plant. People in Manhattan don't have boilers in their house. People in Manhattan have one big steam plant in the Upper East Side, and then from that one big steam plant in the Upper East Side, all the residential buildings in Manhattan are served with steam, which is used for heating and for preparing hot water. And if the flow in such a steam pipe is not regulated appropriately, and you have a transition between gas and liquid and a transition from laminar to turbulent flow, things like that happen. So, maybe 10 years old is the picture, but being able to control steam and the flow of steam and understanding laminar and turbulent transitions and understanding Poisson's laws is eminently important in ever so many areas. Next one I'm going to talk about is heat transport. And I'm not going to talk now about heat transport in terms of radiation. We all know heat transport can work in terms of radiation. There's a sun out there, and the sun is creating a lot of heat, and by radiation comes to us. Or what Hamud is doing, he's looking in his PhD work at trying to do scanning microscopy at low temperatures, and he needs to shield his low temperature objects from the heat radiation, which is ubiquitous at ambient condition. And so it is a different level of radiation shielding has to go. But radiation can transport heat, but it's not really what we're talking about here. And we are also not talking here about convection. Convection, or just the pumping of steam, is another way of transporting heat. It's not really that I transport heat as heat. What I'm really transporting is something hot. So if you put a Bunsen burner under the beaker, then obviously only the water in the bottom of the beaker is getting heated up. And the whole beaker is getting warm because now the water down here starts to get a lower density. The water is heated up, so it expands a little bit, its density becomes lower, If its density becomes lower, then it wants to rise up, because there's heavy water still up here, which wants to then fall down in order just for gravity to equilibrate. And then you get the motion like this one here. That is convection, just as much as a heater like this, which partially radiates and partially makes hot air over here, and the hot air convects out, and that is what he's heating the room. So lots of what we might at first glance think about as heat transport is really either radiation or convection. And we're not talking about this. What we are talking about is only conduction of heat. Now for the conduction of heat, I have an object which is warm on one side and cold on the other side. All the heat needs to travel through this area here in between, so we can again say, okay, there needs to be some cross-sectional area over here in this heat conductor, and then the amount of heat, Q, transported per unit of time is given as the first derivative of an intensive property, temperature, in the system by the position right over here, times the cross-sectional area over here, times the heat conductivity, which is a constant, materials constant. So it is again the diffusion equation, the same kind of equation we had for Courseul's equation in Fick's first law, same kind of equation we had for the equilibration of concentration and for the equilibration of pressure. Now we have the equation for the equilibration of temperature by means of transport of heat. What is really heat transport? What happens? Now there are two things which happen in heat transport. Heat, you know, is, we talked about it way back when, is the vibrations of particles. That we have degrees of freedom, and most degrees of freedom are not the motion degrees of freedom, but the vibrational and rotation degrees of freedom of particles. There are many more generally. So those particles have them excited, they rotate and they vibrate, and they bounce against the nearest neighbors and make them also rotate and vibrate, and they bounce against their nearest neighbors and make them also rotate and vibrate, and so on and so forth. That would be one way of having heat transport, just as this transferring the excitation they have. Another way of heat transport is that if I have an electrical conductor, then I have electrons in that which can move around. And those electrons also can zip very slowly, or they can zip very quickly through that material, depending on how much energy they have in the translation degrees of freedom. And electrons can be much more mobile than nuclei and molecules, and as a consequence, heat transport to a great deal also has to do with the transport of electrons along the object, so that those electrons can then scatter with the material and have, in that way, affect heat transport. Now, the law is called Fourier's law for heat transport, but it's of course just the same looking as all the other ones. The heat conductivity is abbreviated K. We have good heat conductivity for solids, less for liquids, and much less for gases. Kind of makes sense. If you're a solid, if they are all right next to each other, and this vibrates, then this has to vibrate and it moves on. If we are in a liquid, and they're kind of decoupled, all those are close to each other. If I vibrate one, the other one might respond not quite as quickly. And if I'm in a gas and the particles are far away from each other, then it takes a while until one particle is bouncing against the other particle for the heat to be transported. And how long it takes for this particle to bounce against the other one for the heat to be transported depends on the mass of the particles. The heavier those particles are, the slower they move, the slower they transport heat. So if you want to have a gas which transports heat very good, hydrogen, helium, light gases, if you want to have a gas which insulates heat really, really nicely, use a heavy gas like xenon or SF6. That is again a technological application. There are windows where the inner and the outer pane is separated by xenon gas in order to reduce atomic conductivity. If you have a high density of the material, then those atoms are close to each other, and if they bounce each other, then there is lots of momentum, lots of mass involved in the bouncing, and so you have good heat conductivity. If you have very low density material, then there is less bouncing against each other occurring, there are less particles there in the first place, and you have a lower heat conductivity. Styrofoam is very heavy, styrofoam is very light, so it has very low heat conductivity. Copper is very heavy, so it has a very good heat conductivity. Now, there is one more aspect to take into account, that is the Wiedemann-Franz law, which says that if there is electrical conductivity present in the material, then really the electrical conductivity is which transports the most heat. It's really the electrons which are much freer to zip around in a conductor than the nuclear particles which do the heat transport. And then the better the heat conductivity is, the better the electrical conductivity, or vice versa. Wiedemann-Franz law is actually formulated as a certain power of one of them divided by a different power of the other of them is a constant. But really the takeaway message from Wiedemann-Franz law is, if I have better heat conductivity, I'll have better electrical conductivity. If it is the conductor in the first place, or if I have bad good electrical conductivity, I'll have high heat conductivity. So also an example from everyday life. Certainly there is aluminum has a high electrical conductivity and high heat conductivity. If you have an aluminum bicycle and it's cold outside, you put your fingers on it. Lots of things transferred that way. Get really cold fingers really quick. On the opposite side, stainless steel has a very poor electrical and heat conductivity. Like if you have a big spoon or a ladle, then even if you put it in a hot soup, the handle will still stay cool for a long time because the heat conductivity in stainless steel is so low. And so stainless steel also has orders of magnitude worse electrical conductivity than aluminum and copper. Okay, then one can look at all kinds of graphs of heat conductivity. Some of them I've shown here. The material with the best heat conductivity, arguably, is diamond. So people are trying to make materials with even better heat conductivity and even better hardness than diamond, but diamond is pretty much on top of it. If you are interested in making hard materials like diamonds, with similar properties at least that Boniface in the office right above my office, his research group is working on. He also has lots of underrated species. So, then you can see variation of heat conductivity. If you want to really look at how warm are objects, how is the heat being transported in them, it's of course not just Fourier's law in one dimension which you're using. You're using that Fourier's law in three dimensions, how the heat is being transported across even oddly shaped objects. And there are simulation packages where you put in the shape and then the simulation package will solve those differential equations, just like Excel solved newer differential equations there, and figure out how much heat you have. This is for a term like this. But those simulation packages, the most common one of them is COMSOL. The Bonds College of Engineering has a site license for them. So if you take the class over there, you can get access to COMSOL and then play around with this professional software which does that. Okay. Next, the fusion equation. If I'm now not interested in heat, but if I'm interested in charge, Q already. Now Q is charged a moment ago Q was heat, then the amount of charge being transported per unit of time equals the conductivity of a material times the cross-sectional area times the first derivative of the voltage by the position. So in tensor property voltage, X tensor property charge, again I have the diffusion equation. This particular diffusion equation you know already for a long time. This particular diffusion equation is called Ohm's law. But it is really just a diffusion equation. And you should think about electrons in a conductor, just like having gases in a so you can have a kinetic theory of electrons inside a metal, and then you can assign them a velocity and a momentum and the kinetic energy, and then see how they whiz around. It's called the Drude model, D-R-U-D-E. And that explains a lot what is going on in conduction. It doesn't explain everything. It is a model which was developed before quantum mechanics was widely applied, but it's still very good. So if you think about what electrons do and how charge is being transported, think about electrons as gas particles, which are confined to your conductors and where you have different pressures corresponding to the voltages at different locations, and then you can understand, maybe in an easier fashion, what will happen. So with electrons and currents and Ohm's law, it's a little bit complicated because when people define what is the charge, they define positive charge, even though electrons have negative charge, and when they define current, then their current was going from minus to plus, from plus to minus, the opposite direction that electrons move. So the current is always the opposite, they're flowing in the opposite direction of where the electrons move. So always keep that in mind, like in electric chemistry, any number of minuses is always the same. So this is Ohm's law. And Ohm's law usually is written like I'm showing it over here with this conductivity kappa over here, the conductivity kappa over here, Greek letter kappa. But we also know resistivity as a property, and the conductivity of a material and the resistivity of the material is just 1 over each other. So 1 over the conductivity is the resistivity, 1 over the resistivity is the conductivity. If I'm not looking at a material's property, but I rather look at the property of an object, then I can combine the cross-section, which is a property of an object, how much cross-section does it have, and the conductivity of the object and the length of that object is here, all into one number. And if I combine the conductivity and the cross-section and the length into one number, that number is called the conductance of the material. And the conductance of a material is measured in Siemens. Or much more commonly, people think about 1 over the conductance of a material, which is the resistance of a material, and that is then measured in ohms. So if I'm thinking about conductivity, then I have all those electrons moving through an object over here. And we thought about that electrons are like gas particles, like wind or so, going through that conductor. And much of my research in my group these days is about finding materials which are impervious to this wind of electrons. And as a consequence, to form that, the semiconductor industry is getting to smaller and smaller devices. And if you want to wire those smaller devices up by a conventional metal like copper, it will actually degrade in the electron wind of the that goes through. It's called electron migration. And as a consequence, if you have too many electrons going through, you will have the material fail because of that mechanical force. And we are developing materials which are better suitable to that task. Okay, next is ions. Charge can be transported not only by electrons, charge can also be transported by ions. Then we are talking about ion transport. Again, the same amount of charge transported per unit time. Charge transported per unit time is given by now the ion conductance and conductivity of the material times the cross-section of whatever ion conductor you have over here times the voltage drop over the distance. Frequently, if you think about ion conductivity, you define a molar conductivity for the ions, then often called lambda in this way. And the molar conductivity is related to the conductivity by the concentration. So you multiply the molar conductivity by the concentration, you get the conductivity. That works so well. If you have low concentrations, it's pretty good when you have very isolated particles. If you go into higher concentrations, the particles start to interact and you don't get quite the conductivity that you would expect. And we talked a lot about that in the context of batteries in electrochemical cells, how the presence of other particles affect the mobility. Now, the specific conductivity, depending on which kind of material you have different mobility of that material in the liquid. If you have positively charged ions, they are small, they can move readily, their solvation shells are relatively small. If you have negatively charged ions in an aqueous solution, then they have a much larger solvation shell. They, as a consequence, are much more encumbered and moving around, and they move slower. So the conductivity is specific conductivity for positively charged ions is much better than that for negatively charged ions. If you apply a voltage, you can have either travel of the positive ions in one direction or negative ions in the opposite direction, and the positive ions are usually those that travel. Water is a special case, but a very common one. In water, conductivity proceeds in a different way. In water, conductivity proceeds essentially just by the shuttling around of protons. So in water, you always have some hydronium and some hydroxide in it. And if you had a hydronium ion like this one over here, and the water molecule was two lone pairs over there, then the proton over here just needs to move a tiny amount in order to be stabilized the other electrons in that hydrogen-rich bond over there. And effectively, now you have charge transfer. And that way, you have a very high conductivity of in water. If you ever thought about electrophoresis of a certain form of chromatography where you have charged particles and you move the charged particles across the stationary phase by applying a voltage, and in order to affect separation, that then also measures effectively the specific conductivity of the species. Now, that is all really what I wanted to say about the fusion equations, about transport in this class. So we found a large number of the fusion equations. They all have the same shape. We only looked at them in 1D. We only had the first derivative by the distance over here. But of course, in real life, you can have different derivatives in all spatial directions. You can make gradients of that. This is gradient signal over here. And then you have those properties being vectors over here. You don't only have movement of charge or movement of heat or movement of particles in one direction. It goes in any which direction, and so on is best described by vector. So the mass underlying that is then much more complicated, and rather than doing it by hand, I would really advise you to get familiar with software like Console, which would do it for you right away. In Excel, you can again integrate these differential equations in one dimension in a straightforward way, just like we integrated our differential equations, which were governing the reaction kinetics, but in 3 dimensions this will not work in Excel anymore, so we need to specialize. Okay, with that, I'm at the end of this session. I'm also at the end of the chapter on diffusion. I will give you some homework on Monday with regards to that. That will, I think, be homework 16. Of course, it will be bonus homework because anything beyond 12 is bonus, and it will also be the last homework, but that will be on Monday we are going to talk about surfaces.